So the next thing that we're going to do in this section about using derivatives to for kind of applications, or what can we do with all these derivatives that we've done, is going back to limits. So we're going to go briefly back to limits, and we're going to see how can we use derivatives in limits. So the title of this is called L'Hopital's rule. So what is L'Hopital's rule? L'Hopital's rule is a way for us to take limits using derivatives. So the idea behind it is that we're going to be taking the limit as x approaches a of some quotient. So go back to limits, we had a lot of quotients. We're trying to take the derivative, or trying to get a limit of a quotient. If this limit is of the form 0 over 0 or plus or minus infinity over infinity, then we can actually look at the derivative instead of the original limit. So then the limit as x approaches a f of x over g of x is actually just the limit as x approaches a of f prime of x over g prime of x. So that's L'Hopital's rule, is that if our original limit is of the form 0 over 0 or infinity over infinity, and we find those by evaluating each individual limit, then we can actually just look at the derivatives, and the limits will be the same. So that's L'Hopital's rule. The important part of this is that you have to have a quotient. So if we're not looking at a quotient, we can't use L'Hopital's rule unless we manipulate it, and then we will be able to use L'Hopital's rule. So a couple of things here. Other forms that we're going to look at, we could have something like 0 times infinity. So you might have a product. We might have 0 times infinity. If this is the case, change it to be infinity over 1 over 0. Now you don't have to do that, but that's going to be one thing we can do. Why do we do this? It's because g of x is the same thing as 1 over g of x. So all we're doing is manipulating the fraction. So if we have the form 0 times infinity, change it to be the infinity over 1 divided by 0, then this will be infinity over infinity. If it's of the form some kind of exponential, so maybe 0 to the 0, infinity to the 0, 1 to the infinity, something like that. In this case, you're going to let y be your function, and then evaluate the limit of the natural log of y, find the answer to that, and then exponentiate. So those are kind of our three types. We can have the quotient, where it's already of a quotient. I can have a product, which I'll change to a quotient. Or I can have an exponential, which I'll change to a log, which I'll then change to a quotient. In all three of these cases, though, we're going to be using a quotient and then taking the derivative. So that's L'Hopital's rule. Let's do some examples. Example 1. Let's evaluate the limit as x approaches negative 5 of x squared minus 25 over 5 minus 4x minus x squared. Now let's ask ourselves, what's the form of this limit? So if I plug in negative 5 to the top and to the bottom, let's see what happens. Well, if I plug it into the top, I'll get negative 5 squared minus 25, so that's 0. If I plug it into the bottom, I'm going to get 5 plus 20 minus 25, so 0. This is the form that we want. It's 0 over 0. That means I can apply L'Hopital's rule. So instead of looking at this limit, I'll just take the derivative of the top and bottom. So 2x over negative 4 minus 2x. And now let's see what happens if I just plug in negative 5. So I'll get negative 10 over negative 4 plus 10. So what is that? Negative 10 over 6. So negative 5 thirds. So because this was of the form 0 over 0, I could just take the derivative of the top and bottom and then plug in negative 5. Remember, with limits, the idea was to get it until you can just plug in. So get it of the form until you can just plug in. How about the limit as x approaches 3 of the square root of x plus 1 minus 2 over x cubed minus 7x minus 6. Well, let's see what the form is here. So if I plug in 3 to the top, I'll get square root of 4 minus 2, well that's 0. If I plug in 3 on the bottom, I'm going to get 27 minus 21 minus 6, also 0. So this is an indeterminate form, so I can just take the derivative. So the derivative of the square root of x plus 1, that's 1/2 times x plus 1 to the negative 1/2. And then in the bottom I'll get 3x squared minus 7. And now let's see what happens. If I plug in 3, I'll get 1/2 times 4 to the negative 1/2 over 3 times 9 is 27 minus 7. So this will be 1/4 divided by 20. So 1/80. So my original limit is 1/80. Let's do another one. How about the limit as x approaches 0 of cosine x minus sine squared x over sine x? Well, let's see what the form of this is. So the form of this is going to be 1 minus 0 if I plug in 0 over 0. This is not an indeterminate form, so I cannot apply L'Hopital's rule. That means you got to do something else. You could look at the graph or something else, but you can't use L'Hopital's rule. If we actually look at the graph of this function, you'll see that it kind of does this. So the limit as x approaches 0 does not exist, because it goes off towards positive infinity here and negative infinity here. So this limit does not exist. Just because you can't use L'Hopital's rule doesn't mean the limit doesn't exist. It just means you have to do something else. Okay, how about the limit as x approaches infinity of x over e to the x? Well, let's see what the form of this is. The limit as x approaches infinity of x is infinity. The limit as x approaches infinity of e to the x, also infinity. This is of the correct form. Remember, it was 0 over 0 or infinity over infinity. So I can take the derivatives. Derivative of x is 1. Derivative of e to the x is e to the x. And now what happens to 1 over e to the x as x approaches infinity? Well, the denominator is going to get larger and larger, so I'll get 0. Okay. How about the limit as x approaches infinity again of x squared over e to the x? Well, again, as I plug in infinity to the top and bottom, I'll get infinity over infinity. So that's one of the indeterminate forms. So I can take the derivatives. So I'll get 2x over e to the x. And now let's see about this one. If I plug in infinity to the top and bottom again, I get infinity over infinity. Still of an indeterminate form, so I'll apply L'Hopital's rule again. And now as the bottom gets larger and larger, the top stays the same, so I get 0. So you can apply L'Hopital's rule as many times as you need to, just until you can actually evaluate the limit. How about the limit as x approaches 1 of e to the x minus e over natural log of x? What's the form of this? If I plug in 1 to the top, I'll get 0. If I plug in 1 to the bottom, I'll get 0. This is of the indeterminate form that we want. So I'll take the derivative. Derivative of e to the x minus e is just e to the x. Remember, e is just a constant. Over 1 over x. Let's do a little bit of algebra on this. E to the x divided by 1 over x is x e to the x. And now I could just plug in 1 to evaluate the limit. So 1 times e to the 1 is just e. So the limit of my original one is just e. Okay, what about the limit as x approaches 0 from the right? X natural log of x. So what's the form of this? Well, if I plug in 0 for x, I'll get 0. If I plug in natural log, or I plug in 0 for natural log of x going to the right, I'll get infinity, negative infinity, but either way. This is of the product indeterminate form. So even though you're multiplying by 0, which one wins out, the infinity or the 0? It's not really clear. So what you're going to do is the one that's going towards 0. So here that's x. You're going to put that in the denominator as 1 over whatever was going towards 0. These are the same because 1 divided by 1 over something is just that something. And now let's rewrite this just a little bit. 1 over x is x to the minus 1. Now the form is infinity over infinity, and that's always going to be the case. So we can take the derivative. So 1 over x, negative x to the negative 2. Let's rearrange this just a little bit. The top part is 1 over x. I'll bring that out to the front. 1 over negative x to the negative 2 is just negative x squared. So this is just negative x. Once I cancel out my x, and I can plug in 0 and get 0. So this time, the 0 won out over the negative infinity. But whenever you have a product like this, write the term that's going towards 0 as 1 over that function in the denominator. Then apply L'Hopital's rule. Okay, how about the limit as x approaches 0 from the right again? Oops. X to the x over 2. So what's the form of this limit? Well, as x goes towards 0, I just get 0 for x. Also, x over 2 goes to 0. So there's my form. This was one of your indeterminate forms. This was in that part 3 that we did before. So what I'm going to do is I'm going to let y be my function. Then I'm going to look at the natural log of y. So that'll be the natural log of x to the x over 2. Now apply your properties of natural logs. I can bring this x over 2 out. So that's the limit I'm going to look at. So instead of looking at my original limit, I'm going to look at this limit as x approaches 0 from the right. So let's go to the next page. I'm looking at the limit as x approaches 0 from the right of x over 2 natural log of x. And this was the limit of the natural log of y. What's the form of this limit? Well, that's 0 times infinity. So remember, what do we do whenever we have 0 times infinity? I take that term that's going to 0 and I write it in the denominator as 1 over it. Now let's make this a little bit nicer. This is natural log of x, 2x to the minus 1. This now is of the form infinity over infinity. So I'll take the derivative of the top and bottom. So 1 over x, negative 2x to negative 2. And now let's do some algebra. So this is 1 over x times x squared over 2 x's are going to cancel, so I'll get x over 2. As x goes to 0, that just goes to 0. But we're not done. This was the limit of the natural log. That's not what I want. So what we just found is that the limit as x approaches 0 of the natural log of y is 0. But we want the limit of just y. That was my original function. So what I do is exponentiate. So e to the 0, which is 1. So what did I do here? Instead of looking at my function, I looked at the natural log of my function, took the limit using L'Hopital's rule, and then exponentiated in the end. Let's do one more of those. So the limit as x approaches 0 of x to the sine x. So what's the form of this limit? Well, as x approaches 0, I'm going to get 0. As x approaches 0 of sine x, that's also 0. So this is of the indeterminate form, 0 to the 0. So I let y be x to the sine x, and then I look at the natural log of y, which is the natural log of x sine x, which is sine x natural log of x. Okay, now I'm going to look at this limit. So I'm looking at the limit as x approaches 0 of the natural log of y, which we just found was the limit as x approaches 0 of sine x times natural log of x. What's the form of this? Well, as I plug in 0 to both, I'll get 0 times infinity. Remember, what happens when we have a product that's 0 times infinity? You take the term that's going towards 0, so this one, and I'll write it as 1 over that function in the denominator. But now, what is 1 over sine? 1 over sine is cosecant x. Okay, now the form is infinity over infinity, and this is always going to happen. So I'll just take the derivative. So I'll get 1 over x for the derivative of natural log. And now what's the derivative of cosecant x? That would be negative cosecant cotangent. So far I have that I'm looking at the limit of 1 over x, negative cosecant x, cotangent x. So I've taken the derivative, and let's see if this has helped us any. Now what is negative cosecant cotangent? Bring my 1 over x out. Negative cosecant is going to be negative 1 over sine. Cotangent is cosine x over sine x. So all we're doing is really moving stuff around right now. If I simplify this, this is going to be 1 over x times 1 over negative cosine x over sine squared x. Now whenever you do 1 over a fraction, that just means flip the fraction, so this will be times negative sine squared x over cosine x. So this is, now that we've simplified it a lot, negative sine squared x over x cosine x. So we took the derivative, and this is where we're at. What's the form of this limit? If I plug in 0, again I'll get 0 over 0. So let's take the derivative of the top and bottom. The derivative of the top, that's going to be the chain rule. So I get negative 2 sine x times cosine x. Take the derivative of the bottom using the product rule, so I'll get cosine x plus, I should say minus x sine x. Now what happens when I plug in 0? I get 0 over 1, which is 0. Now that's not my problem though. Remember, I was doing the limit of the natural log. So that tells me that the actual limit that I want is e to the 0, which is 1. So whenever you have one of the indeterminate forms with the exponent, look at the natural log, then exponentiate in the end. If you have a product, take that term that's going to 0 and put it in the bottom. So maybe we'll do one more of those. So the limit as x approaches infinity, e to the minus x, x cubed minus x squared plus 9. What's the form of this limit? Well, e to the minus x as x approaches infinity is going to go towards 0. This polynomial is going to go towards infinity. So I'm going to rewrite the limit and take the one that's going towards 0, so this one, and put it in the denominator. So I did 1 over e to the minus x. Before I actually evaluate this, let's see if we can simplify it just a tad. 1 over e to the minus x is just e to the x. Now this form is infinity over infinity, so I take the derivative. So 3x squared minus 2x over e to the x. This form is still infinity over infinity, so take a derivative. So 6x minus 2 over e to the x. This form is still infinity over infinity, so I'll use L'Hopital's rule. And I'll put a L'Hopital's rule on all these. So I get limit x approaches infinity of 6 over e to the x. Now the top is staying constant, the bottom is going towards infinity, so I just get 0. And on this one I didn't take the natural log, so I don't have to worry about exponentiating. So there's L'Hopital's rule. You always want a quotient, so you got to write everything as a quotient, so that's what we've been doing.